like now. And I'm just going to make sure that it's okay. The mic is going. All right. All right. So we're going to focus on CNF or conjunctive normal form today, because I'm going to give you an assignment um, that involves CNF or conjunctive normal form. So what I'll do is I'm going to go through some of the boring stuff. Like you can see a lot of text here. So I'm just going to have to go through some of this boring stuff here, to basically establish that, yeah, we kind of know that CNF is complete, meaning that you can express any Boolean expression as a conjunction of disjunctions of the variables. So we're going to go, we'll talk about that first. And then we'll talk about the techniques, of what rules are usually applicable, how you can use those. And then we'll go through maybe one example, that's also in the module itself. And then we'll answer any questions that you guys might have. So are there any questions before I start on CNF? No questions? Okay. All right. So let's start with what is a CNF first. So a CNF is um, basically okay. If you think about a Boolean expression that involves certain quote unquote variables like p, q, r, s, t, then what you can do with a Boolean expression is you can also always build a truth table. Okay, first of all, does that make sense? Okay, so with a truth table, so I'll give you a very general example. Maybe just using a text editor. And I'm pretty sure I have one open from before. Yep, I just passed it. Okay, there we go. All right, so let me start on a new tab. There we go. All right, so let's just say that we have three variables, p, q, and r. Okay, so we have p, q, r, and then we have an expression of um, not p implies q and not r. Okay, it's just a random expression. Okay, I have no idea why I came up with this one, but that's what we have. So the first thing is we know each Boolean variable, p, q, and r, each one can be true or false. But because they're independent, so that means when p and q are both true, r can be true or false, etc. So that means we have 8 rows in this case. So we have 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, and then just kind of repeat everything with p being true this time. And the last one is 1, 1, 1. And then for each row, we can say, okay, whether the expression is true or not. In this case, because not p is on the left-hand side, so that means there are 4 rows that are really easy to figure out, like these 4, because when the left-hand side of a imply is false, then the implication itself is going to be true. So that's the easy ones. And then for the first 4 rows, we kind of have to look at the right-hand side. We need Q to be true. We need R to be false. So that means only this one is going to be a true, and then for all the other ones, they're going to be false. Is that okay? Does everybody understand how I populated the value within um, the truth table? Okay. So now the next question is, I look at this and go like, okay, theoretically speaking, this has to be representable using CNF. Now, why is that the case? Because what we can do is now we can just focus on the rows where the expression is returning true. So I'm going to highlight the rows that we are talking about, or the rows that I am talking about, such as this one here. Okay. So if this one is true, and I need one expression that is true, but only for this row, what is that going to look like? Let me say that one more time. If I want an expression that is true, but only for this row, it's going to be false for every other row, what expression is going to be true, but only when P is false, Q is true, and R is false? Yep.
Not P and Q and not R.
Yep. So for this one, we have not P and Q and not R. That expression, this conjunction, is true, but only for the third row. It's going to be false for everything else. So for the same reason, I can look at these four and kind of come up with the same thing. I'm not going to work with the redundancy and whatnot. I'm just going to go for a very mechanical translation. So in this case, it's going to be P, not Q, R, not R. And then for this one, it's going to be, so every time you see a true, it is non-negated. Every time you see a false, it's going to be negated, and so on. So here we have the complete table. So we have P, Q, not R, and then the last one is PQR, which is basically the conjunction of P, Q, R. Is that okay? So now we can um, take these five and then make a disjunction of it. So now we can look at these five, and then we can have not P, Q, not R, or P, not Q, not R, and then we have P, not Q, R, and then we have P, Q, not R, and then we have P, Q, R. This is not exactly what we want. This is sort of, in a way, opposite to what we want, because this is a disjunctive normal form, where things are exactly the opposite. We have a disjunction of conjunctions, and for each conjunction, we have either a variable or the negation of a variable. Is that okay? But do you see how, yeah, we can make it happen? So the thing about true and false, I mean, not true and false, the thing about conjunction and disjunction is they are dualities. They're basically dual of each other. If you give me one and a negation, I can give you the other one. It's really easy to use De Morgan's law to work with that. So that means, in this case, if you want to start with a CNF or conjunctive normal form, you want to rule out things. Because with a conjunctive normal form, you are looking at the conjunction of disjunctions. So you want to use disjunctions to include things, and then use the conjunction to say we're only looking at the intersection of those things. And then the other thing that is here is you can look at the Morgan's law is one of the ways to do this. So let me go back to the notes here. This is because any Boolean expression involving n variables, so we have 3 variables in the other case, can be represented by a truth table that has 2 to the power of n rows. In this case, we have 8. There are n plus 1 columns, n of them corresponding to the n variables, and the extra one corresponding to the value of the expression based on the values of the variables on that row. So that's exactly what we have here. This is the truth table. We have the 3 independent variables. We have 2 to the power of 3, which is 8 rows, and then we have 4 columns, 3 for the variables and the 4th one for the expression. Any additional item to a conjunction further restricts the value of the original conjunction. The most concise way to express this is for any Boolean expression P and Q, P and Q implies P, and likewise P and Q implies R. So let's look at these two implications first to make sure that we understand what they mean. P and Q implies P. Is that always going to be true? Now you can use a truth table to prove that, but you can also conceptually think about this and prove that also. So with an implication, there are 3 ways to make an implication true. Okay? The left-hand side is false, then the implication is automatically true. The only one that is tricky is what if the left-hand side is true. If the left-hand side is true, the right-hand side also has to be true. Does that make sense? So in this case, we're only concerned about the left-hand side being true to begin with. So if you think about it, if the left-hand side is true, which means P and Q is true, doesn't that already say that P has to be true? So that's why P and Q as a conjunction implies P is always true, and so is the other one, which is basically just playing with the commutative law of conjunction. Is that okay? All right. So all this is saying is it is not possible for P and Q to be true, but P is false, or it is not possible for P and Q as a conjunction to be true, but Q is false. I mean, it really makes sense, just based on how conjunction is defined. So this means each disjunctive term, disjunction element in a CNF turns more of the rows of the truth table, corresponding to the expression false. Once a row is false, an even longer conjunction cannot make it true anymore. So let I be an integer from 1 to n, where there are n variables, and each variable is represented by v of I. So that is basically just a way for me to iterate through the variables. Instead of referring to the variables as p, q, r, it is now v1, v2, and v3. Just because this way, it is easier for me to specify a quote unquote loop or control structure to iterate through all the variables. Furthermore, let T of I be a term that is based on variable V of I. So T of I can be V of I or the negation of V of I. Is that part okay? So we have first variables, and then we have a term. A term is either a variable or it is the negation of a variable. It can be one or the other. Is that okay? It's just a terminology right now at this point. Or it can also be false. Okay, so a term can also be false. Then each DE can be seen as a disjunction of a term corresponding to variable I. This notation, the big V notation, is just an or, but iterating as the index variable I goes from 1 to n. So we are looking at T of 1, T of 2, and T of 3, where T of whatever is either the variable V of I or the negation of the variable T of I, V of I, or just false. So are we still okay so far? Okay. So with three variables, we are looking at something like this. We have an OR, and it's an OR of three T of I's. Each T of I, T of 1, T of 2, and T of 3, each one can be one of three possible things. So it can be V of 1, which in our case is P. It can be the negation of V of 1. It can also be false. But in this case, you have to choose one. Okay? And T of 2, same thing, except it applies to V2. T of 3, the same thing, it applies to V3. So it's just me formalizing what a term is and also what a DE or disjunctive element looks like. Applying De Morgan's law, each DE can also be seen as double negation, excuse me, the double negation of all the terms ORed together. So is that okay? I mean, let me ask, is everybody okay with this expression here? It's really the same thing as that expression over here, because double negation cancels each other out. Are we okay so far? So you might ask, but why do you double negation when it doesn't change the meaning or the value of the expression? Because double negation gives me a chance to apply De Morgan's law. Do you guys still remember De Morgan's law? At this point, it is important to remember De Morgan's law, because even though I can show it again, but in order to understand how it is applied in a derivation like this, it's really much more important, much more efficient to have the De Morgan's law remembered. So De Morgan's law can be seen as a distribution of negation. So when you have a negation of an OR, then you can distribute the negation into the individual things being ORed together. Is that okay? That's basically the essence of De Morgan's law. It is the distribution of negation. A negation that applies to an operator becomes the negation applied to whatever that operator is operating on, with the twist that if you originally has an OR, that operator would have to become an AND. And if you start with an AND, then it has to end up as an OR. Is that okay? All right. So applying De Morgan's law, I can now rewrite the inner part here, the negation of a big OR becomes a conjunction of the negation applied to the individual term, the outer negation stays over there because I'm not doing anything with the outer negation. Are we okay so far? Do we have any questions about this particular derivation? Is that okay? All right. So let's talk about the negation of a term ti. If ti, the negation of ti is either vi, the negation of vi, or one, it can be one because the negation of zero is a one. Is that okay? And the bottom line is the negation of the conjunction of these terms turns at least one row in the truth table false. Does that make sense? So instead of trying to make a row true, I am trying to make the rows false. Let's take a look at the example that I just showed you, and we are going to pick a row that was false to begin with, such as pick this one. Okay, so I'm just looking at this row here, and in order to make an expression that is false, I can now do something just like last time. So I'm going to look at um, not P, not Q, R in this case. This is a conjunction. But when you look at this particular conjunction, it is true for the second row. Is that correct? Because on the second row, P is false, Q is false, but R is true. So when you look at the conjunction of the negation of P and the negation of Q and R that is not negated, that conjunction is true. So if I want to put a negation on top of everything like this, then this expression is false for that specific row. Are we okay so far? Okay. So instead of focusing on making the value of a row true, I'm now focusing on making a row false. I'm looking at all the rows where the value of the expression is false, and I'm creating all of these kind of weird looking negation of a conjunction. But I'm going at a certain place, okay? I'm trying to get to a certain point. So let's go back here and continue to read and see where we are going. So given any truth table representing a general Boolean expression, one can craft specific terms like this to specify rows where the Boolean expression evaluates to false based on the values of the variables. As a result, any Boolean expression can be expressed equivalently using a CNF. All right, so let's take a look at the truth table that we have and find out how this is applied. So I'm switching back here. So now I'm looking at the first row, which has a value of false. This one is pretty easy. Not P, not Q, not R. I'm now erasing the ones that are true to begin with because that is no longer what I'm looking at. But I want to um, basically make an expression to make a particular row false. So this is not P, Q, R like so, and then the rest I'm going to erase them because I don't want these to be confusing our expression here. All right, so right now we have three expressions. Each expression is false, but only for the row that it is on. It is actually true for all the other rows. Let me further explain what I mean by that. If you were to evaluate this expression here for anything other than the first row, the outcome of the expression is going to be true. Does that make sense? I hope so. Okay. And the same thing applies to the second one. If you evaluate this expression, including the outer negation, it is going to be false, but only for the second row. For every other row, it's going to be true. Is that okay? And obviously, the same thing for the third one. So now the question is, instead of using a DNF, which is a disjunctive normal form, now I end up with, okay, I'm going to do copy and paste just so that I do not make any mistakes. So we copy and paste this one, and I'll leave behind a symbol that is not defined yet. Okay, so I'm just going to combine. Oh, that's the same. Um, not P, not Q, R. And then we have the negation of not P and then Q, R are not negated. Okay, so now I look at these three, and then I ask, well, what about these three? Each one is only turning one particular row false, but every other row is going to be true. So if I explicitly say and, okay, let me just use the regular proper and here. So if I use a proper and here and a proper and here, what do you think this overall expression going to specify? Yep.
When the expression is true.
Right. So this entire expression, okay, let me highlight which portion here. This entire expression is going to be the same, it's going to be equivalent to not P implies Q and not R. In other words, okay, if I were to copy this and say, okay, let's make another column for this rather long and tedious expression, I can now expect this expression to be identical to the fourth column. Okay, so first of all, does that make sense to you? Okay, if it doesn't make sense to you, how do you look at this and go like, well, I have no idea whether TAC is lying, which I'm very good at, or whether I'm actually telling you the truth. So what are you going to do? Evaluate, right? The truth table is already here. All you need to do is to evaluate for that particular column. Is that okay? Does that make sense? Okay. So I'm going to pick a random row. I'm not going to do it for every single one. I'm just pick one single random row, and I'll even let you guys pick which row do you want me to pick, just to spot check that this expression is going to come up with the same value as this expression here. You have 8 choices. 7. All right. So the second to the last, like this one. All right. So in this case, P and Q are both true. R is false. So if P and R are both true, but R is false, so that means this is going to be false, which means this entire thing is false, but because of the negation on the outside, this whole thing is going to be true. Does that make sense? This one is also going to be true because I know that P is true, which means not P is false, but because not P is in the conjunction, that means the entire conjunction is going to be false. Not false is true. So now I have proven that this expression is going to be true. So looking at the last one, kind of the same deal, because we have not P in the conjunction, which makes the entire conjunction to be false. And because we have a negation of the entire conjunction, it is also true. So we end up with true and true and true, which means for the row that we have chosen, it evaluates to true. So what you need to do, if you're not convinced that the two expressions are actually identical, is to do this for every single row. Then you will see for all 8 rows, the implication expression is identical, is going to end up with the same value as the really tedious thing that has a bunch of ands. And then each and, inside each and, is the negation of an and. Then you guys are going to say, but Tag, you did say something about disjunctive element. I see no disjunction in this particular expression. In other words, when we look at this expression here, there are no disjunctions. I mean, this is a negation of an and, this is a negation of an and, this is a negation of an and all of those are connected by and more, even more ands. So what is the deal here? Where are our disjunctive elements? Yeah, go ahead. De Morgan's law, because every time we see the negation of an and, we can say, we can see we can distribute the negation to the inside, but all the operator of and has to be changed to an or. That means what that means is this expression here. Okay, let me go to this expression. If I apply the Morgan's law 3 times, it becomes not P or not Q or not R. Yes, I know I can put it in a simpler way, but I want to keep it this way for now. And then we have not P, not Q, not R. Yep,
You missed the first P.
I missed.
Yeah, you missed the first P.
Oh, P. Oh, forgot to. I didn't type P on the keyboard. All right, thank you. And then the last one is going to be not P or not P. Oh, I forgot the ORs too. These are all supposed to be connected by ORs. And then the last one has not P, not Q, and not R. There we go. And then once you get rid of the double negations, then you end up with something that is nice, right? Because double negation just kind of goes away, and now we end up with this conjunctive normal form. Is that okay? Do you guys see how I converted from the truth table, looking at which row is false, and then just go through a few transitions to come up with the conjunctive normal form. Which part of this is conjunctive normal form? The last thing that I worked on. This is in conjunctive normal form. And for those of you who say, I really don't want to mix and match, the plus and the double ampersand operator, fine. We'll do a global search and replace by hand. And now we have this. Okay, I'm going to pause here to see if there are any questions. Because this is a demonstration, okay? It is not a proof, but it is a demonstration that you can turn any Boolean expression into conjunctive normal form. If you can give me a truth table, I can give you the conjunctive normal form. Does that make sense? All right? So there's no question, there's no dispute of how you can turn an expression into the equivalent conjunctive normal form. The only question that is left now is, besides doing it in this way, which is a truth table method, and it's kind of tedious, can we use Boolean algebra to do the same thing? The answer is yes. Okay, so I'm going to demonstrate that next. Is how do we use Boolean algebra to come to the same conclusion of this is the CNF corresponding to the original implication operation expression. But I do want to make sure that we do not have any questions at this point before proceeding with the Boolean algebra method. Yep.
Why do we need to convert it to CNF?
Because resolution works really well with CNF. Because what resolution is trying to do is to look at all the DEs, all the disjunctive elements, and it will try to do a match. You get a match if one DE has a variable and another DE has the negation of the same variable. Then they match, and once they match, you can now concatenate the two DEs, but remove the element that is quote unquote serving as the connector. And then the resulting expression is going to have one fewer variables. And if you keep doing this, then the new expressions that you're creating, they get simpler and simpler and simpler until it becomes nothing, which is false. And then at that point, you have a contradiction. Mm-hmm. So that's a very good question, because right now we are kind of lost in the pine needles right now because these are very mechanical processes. But once we get back up to the tree or the branch level, then it becomes a little bit more obvious why we need CNF to begin with. All right, so any other questions? That was a very, very good question. Any other questions about how I took a truth table and converted the truth table into a CNF? No questions? All right, well, if there are no questions, I'm going to use algebra to basically do exactly the same thing. So we have not P implies Q and not R. So the first thing I usually do is to get rid of the implication. So the implication becomes the negation of the left-hand side. And then we have a or the right-hand side. So we have Q and not R on the right-hand side. And then at this point, I'm going to do some simplification, which is double negation, it goes away. And then we have Q and not R. And if you're concerned about not knowing the priority of the operators, you can always put in extra parentheses. So I can do it like this. But basically, when you look at negation, negation has the same priority as a arithmetic negation. In other words, it has the highest priority. It always applies to whatever is immediately to its right hand side. And then conjunction has the same priority level as multiplication, and disjunction has the same priority level as an addition. So what you normally understand as the operator priority in normal arithmetic still applies here. So we look at this and go like, this seems to be opposite to what we want, because at this point it is a DNF, because the last operation is a disjunction, and then the components are either a variable all by itself, or it is a conjunction. Well, that makes it very easy to do the conversion, because now we just need a distribution. So we have P plus Q and P plus not R. That is how we apply distribution. So if you look at this from a normal arithmetic standpoint, it does not make any sense. But Boolean algebra allows distribution to be done in both ways. In normal algebra, in normal arithmetic, you can only apply distribution when you have a product of sums. Then you can distribute the sum into products into a sum of products. But in Boolean algebra, it works the other way as well. Okay, so now we have a CNF, because this really translates to P or Q and P or not R. So if I were to use the C++ operators, that's what it's going to look like. You guys look at this and go like, tack, we got a problem, because we do not see how these two expressions are the same. We got this expression, right? And that is supposed to be representing the same column, the original expression. And now we have this expression here, which is also supposed to be representing the same thing. And I forgot one thing. I forgot that we have a student who's online. So let me see if I can get back to him right now. All right. And, all right. So there we go. Okay, back to here. All right. So now we have two expressions that do not look alike, but we want to know, really establish that these two are exactly the same. Let's take a look. So we look at P or Q or R, and then we have P or Q or not R. Actually, of, of resolution, because you asked earlier, why is this important? It's because we can now apply resolution. Okay. So what I claim is, once we apply resolution, these two expressions here, these two expressions will basically combine to this expression here. And that's being done through resolution. All right, so if you have forgotten what resolution is trying to say, we'll go back to the earlier discussion of resolution. This is resolution. So resolution is saying, give me a conjunction, okay? And in the conjunction, I need each term of the conjunction is supposed to be a disjunction. And of the disjunctions, I need one thing, okay? If one side has some expression called psi, then I need the other side to have exactly the negation of psi. I don't really care about the rest of the disjunction. In other words, phi can be whatever, okay? There's no requirement. And rho can be also whatever. But if you give me a conjunction of two disjunctions, where one disjunction has psi as a part of it, and the other disjunction has the negation of the very same psi as a component of it, then I can now say, this is implying that phi or rho. In other words, the conjunction part is gone, and then the psi completely disappears. So psi disappears from the first expression, and the not psi disappears from the second side. Now, why this works? It has to do with this proof here. Okay, so this proof shows that this implication always holds. So the next question is, how do we apply this? So to show you how this applies, I'm going to show this at the top of the screen, and then we'll see if we can display that at the same time as we display this. So what we are looking at here, okay, if I were to describe um, which part is phi, this part is phi. So phi is, let's see, yeah. So we can look at this part as phi. So phi is this part, and r by itself is basically our psi. So this is our psi, and this part here, even though it really is the same thing as psi, we will call this rho this time. And the not r is the negation of psi. This is not psi. Okay, so I'm just going to pause here and see if you guys recognize, you know, if I need to fit these two in a conjunction into the left-hand side template of the implication, this is how I can set up the Greek letters. Does that make sense? Is that okay? So structurally speaking, okay, let's talk about structurally speaking what we are matching here. We are matching the and with the and. We're matching this particular or with this particular or here. We're matching this or as, as this particular or here. We are looking at psi and say, I can make r, the expression r, our psi over here, which is just a placeholder. So if r is psi, then not psi is just going to be not r. So that's why we can set up psi and not psi as r and not r respectively. And then the rest of each disjunction, which in the first one is this portion, I'll just call this phi, which is basically saying, the rest of this disjunction, I don't really care what it is. And then on the other side, I look at the rest of the expression, not counting not r itself. It turns out to be exactly the same thing, but from my perspective, it is simply known as rho, which is also just a placeholder to say the rest of that disjunction, I don't really care what it is. Is that okay? So now, according to resolution, I can now say this part here, okay, let me just kind of match up the positions. I can now say this entire part here is just basically becoming phi or rho, okay? But since phi and rho are exactly the same thing, phi is P or R, rho is also P or R. So when you have the same thing and you're ORing it together, you just get the same thing back. So that's why, this whole thing, once we substitute what rho and R, what phi and rho are representing, this really just boils down to P or Q, which is exactly what we have here. Is that okay? So this is after using resolution, we can arrive to exactly the same place as what we have here. What about the P or not R? This is the P or blah blah or not R. So what do we do to end up with P or not R? We can apply resolution again. But which two disjunctions are we going to use in the conjunction to perform this particular resolution? So the question is, in the new expression, we have this term over here, which does not match any term of the expression as a result of mechanically converting the truth table into a CNF. The question is, can I claim that some components of the highlighted CNF is implying P or not R? That is the question. And the hint is we're going to apply resolution again. The question is, which two disjunction am I using, and which variable within those two disjunctions is going to serve as the connector? So, what do you think? We can just call this the first, and then we call this the second, and then we can call this the third disjunction. So you can now tell me which two would be used in the resolution. Yeah, the second and the third, right? Exactly. So when you look at the second versus the third, they differ by one single term. Okay, remember a term is either a variable, the negation thereof, or in this case, a zero, a false. Okay. So in this case, we can see they both got P. Okay, so P cannot be used as the connector. They both got not R, so not R cannot be used as the connector. But one has Q and the other one has not Q. So this time, Q is serving the role of psi, and then not Q is serving the role of not psi in the resolution rule. Is that okay? The rest of the disjunction is simply known as phi on one side, and is simply known as rho on the other side. So psi and phi and rho are basically just saying the rest of that expression. Is that okay? So after we perform resolution of these two disjunction elements, then we end up with this, because the connecting variable, which is Q, and its own negation, it disappears. Are we okay so far? Yes? So I went through a lot of explanation to show you, how we can actually apply resolution in this case. And in the end, what I'm really claiming is this expression here, which is mechanically generated based on the truth table, which means it can be very much redundant, is actually the same as this expression here, which is derived using Boolean algebra. So once again, we have this nagging question of, we have no idea whether Tak is lying or whether he's telling us the truth. So how do you make sure that this expression, the one that is being highlighted, also is going to have exactly the same true and false as the original expression, which is an implication? Add one more column to the truth table and work it out. It's going to be very tedious and boring, but at the end of that exercise, you will get this feeling that, oh, so they really are exactly the same thing. In other words, let me highlight which portions I'm referring to as being quote unquote the same. So what I'm claiming at this point is this original expression using implication and conjunction and stuff like that, it is not in conjunctive normal form, is the same as this expression here, which is a mechanically generated CNF based on the truth table. And that turns out to be exactly the same as this CNF, which is derived from using Boolean algebra from the original expression. Those three are exactly the same. They would give you the same true and false value in the truth table. So are we okay so far? Yep.
Can you make a CNF using the true um, like values of the implication?
Not easily, because if you focus on these specific roles, then you end up with a DNF, a disjunctive normal form instead of a conjunctive normal form. You can probably get a mechanical process to convert those two, but it's not going to be as natural as doing it this way. To look at the rows where you have a value of 0 and then come up with the conjunction that makes the row true and then put a negation on the entire conjunction, and therefore giving you the ability to apply the Morgan's law and turn it into a disjunction. And I think I got a message from Discord. Let me double check. Oh, okay. Oh, okay. Let me go back in again. Oh, I just messed up OBS. Alrighty. Hmm. Darn it. Oh, okay. Never mind. All right, no problem. All right. OBS is still recording, so I think we are good there. All right. So I do apologize for the um, distraction. All right. So what was the question that was trying to answer? Oh, looking at the true rows instead of the false rows. So the answer is probably doesn't work out easily that way. Um, so are there any additional questions about the two methods going from a particular expression, any arbitrary well-formed formula, to the equivalent conjunctive normal form like this, which is mechanical, or like this one, which is the result of applying Boolean algebra? No questions? Okay. So I do have to be honest. Um, this is the first semester that I actually talked about using the mechanical method, which is basically saying if you give me, just generate the truth table, and for all the rows that have a value of false, you generate the negation of a conjunction, and then use the Morgan's law, turn those negation of conjunction into disjunction, and then have a conjunction to connect all of those disjunctions together, then you have your CNF. It's a very mechanical process. So your homework assignment is going to involve, a certain expression, and you're supposed to turn it into a conjunctive normal form. And this is the first semester that I actually talk about the very mechanical method, like what I just described here. So you can use that method in your homework assignment. Okay? Instead of using Boolean algebra, you can use that method also. So it's your choice. Okay? You can say, I want to try out my Boolean algebra skills. That's fine. On the other hand, you say, but I don't want to use algebra. If there's a mechanical method that guarantees to work, even though it's a little bit tedious, a little bit mechanical, I'm still going to use the mechanical method. That would be okay as well. Is that okay? All right. So I am going to show you your homework assignment, because now that we have talked about this portion, I think I can show you the homework assignment, which is simply named CNF. So in this particular homework assignment, you are to convert this expression here into a single CNF. So the first thing you want to do if you want to use the mechanical method is to count the number of independent variables. How many do we have here? We have P, Q, R, S, T. There are 5 independent variables here, which means how big is your table? Well, how many rows do you end up with?
32.
32. Yep. So you end up with 32 rows, but it doesn't mean your CNF is going to have 32 terms because we're only concerned about the rows that are false, right? So you have to basically you have to create the table first, and then you look at how many rows are false because if I mean you can probably write a program to do this entire thing, right? So you write a program, you use an array of variables, and then you generate the truth table mechanically, and then you go through each row that gives you a value of false, and then you look at what value of the variables is corresponding to that row, and then you can generate the DE or the disjunctive elements, accordingly. And then at the end of the program, you concatenate all those strings using the conjunction operator as the connecting operator, and you're all done. You can do this, probably in a 10-line program using JavaScript. C++ is going to be more cumbersome because JavaScript has a lot of really cool features to work with arrays that C++ does not. Are we good so far? All right. So this is a nested application of implication too. There's an implication here, and then it's inside this pair of parentheses, and there's another implication here to imply the other side. So just be very careful when you look at the nesting of the parentheses. And then for your answer, I think this basically says you can use the shorthand that I have been using for a while, which is to use exclamation point for negation, and then for conjunction it looks like multiplication, and then for disjunction it looks like addition, which means the original question can now be reformatted in a more concise way like this. So it's up to you. This part is up to you. Okay, how you want to do this derivation. If you choose to use the mechanical method, I want you to show me the truth table. So you have to show me the truth table, look at all the rows that are zeros, okay, and then make a conjunctive normal form based on what I have just described in today's class. And I'll give you a week to do this. So let me do the edit and give you 1 week to do this. So 1 week from today is going to be the 17th, October 17th at 3 p.m. There we go. All right. Any questions? And by the way, you only have to give me a CNF. It doesn't have to be optimized or simplified. Okay? It just has to be correct. Are there any questions about this part? Which is from the perspective of a branch instead of the pine needles. It's simply saying, give me any Boolean expression that is well-formed or syntactically correct. We can generate a CNF that has the same, that is identical, that is equivalent to the Boolean expression. Is that okay? All right. So now I think we are ready to go back to talk about proof by contradiction. We started that discussion using the pigeonhole principle. So today we're going to use another example to illustrate proof by contradiction. So let me go back to the discussion of proof by contradiction. There we go. So this is proof by contradiction, which is starting off with the reason why it works. Okay, so there's a corollary, and there's the actual proof of why proof by contradiction itself is going to work. In other words, this is a proof of a proof technique. Are we good so far? It is very important that we prove that the proof technique works, because otherwise we have no idea whether the technique, the result of applying the technique is going to be useful or not. So the first example we have is the pigeonhole principle. So I'm going to give you one extra example today, which is related to, let me look at the time, which is related to finding out whether a number is prime or not. Okay, so seemingly this has nothing to do with what we have been talking about, except for proof by contradiction. So let me show you what I mean by, what I said earlier, using, finding whether a number is prime or not. So I'm gonna pick a number, and I have no idea whether it is prime or not. Let's just say that it is 2,333. I have no idea whether it's prime or not. Let's hope it is. Okay. So the question is, how do you test whether a number is prime or not? You have your usual rules of thumb, right? If the least significant digit is a 5 or a 0, then you know the number is divisible by 5. If it's a 0, 2, if it's an even number, you know it's divisible by 2. So there are certain rules you can use to kind of fast track to see if the number is a multiple of very specific numbers. In this case, you can also add up all the digits. So you add 2 to 3 to 3 to 3. The sum is 11, which is by itself not divisible by 3. So I know that 2,333 is not a multiple of 3. So we know right away it's not a multiple of 2, it's not a multiple of 3, it's not a multiple of 5. Is it a multiple of 7? I don't know. I mean, we have to test it. So I'm not going to waste my time to test it. I'm going to use a spreadsheet to do it. Just like you guys already know what I would do, right? Because I like to use spreadsheets to do all kinds of work. In my CISP440 class, I also use a spreadsheet to make an assembler. That's how useful a spreadsheet can be. It's really cool. All right, so make a new spreadsheet, and I will title you can access the spreadsheet, by the way, if you have your computer um, already open to the Canvas site. So the question is 2333 a prime number? All right, so I'm going to look at 2333, and then we'll look at the mod of, in this case, it is $1 divided by the row number of this column plus 1, which in this case is 2. And this is basically, okay, so let me show you the trick that I just did. So I used the mod operator. You guys already know what a mod is. It's basically the percent operator. $1 is referring to the cell A1, but it doesn't change the row reference as I copy this equation down. So that's why the dollar sign is important. It means absolute, okay? It means do not make this relative to where I copy and paste the formula. And the row in parentheses is reporting the row number. A spreadsheet is not zero oriented, it is one oriented, which means the first row is literally row 1 and not row 0. So I use the row number and add 1 to it, which means the first potential factor is 2. I'm just testing whether this number is divisible by 2. So I can improve this equation and simply say if this is not 0, then we can just report that as a truth value, as a Boolean value. So this way I can simply look at the truth value and say, nope, this is not divisible by 2, and we just have to look keep looking, keep looking. So the question is, when do I stop? And I have no idea whether 2,333 is really a prime number or not, but I want you to think about when do I stop? Assuming it keeps being true this entire time, when do I stop? Okay, there are a few really obvious choices. We can stop when it is testing whether it is its own factor, right? In other words, on row 2332, it would be a false because an integer is always divisible by itself except for 0, right? But that's kind of tedious. I don't think we have to go that far, right? And some people are going to say, well, we can all go all the way to about this number divided by 2. I mean, that should be clear enough, right? Well, even that is a lot of numbers to go through. So what is the actual number that at which point I can stop? I'm going to say about row 50. It's going to be before row 50. So we'll go ahead and check out whether it is actually a prime number or not by keeping this up until about row 50. So I think row 49 is going to be way better than good enough. All right, they're all true, which means I think 2,333 is indeed a prime number. I'm pretty sure some of you can just Google search literally, literally, which means you type exactly, verbatim, is 2,333 a prime number? And I'm pretty sure Google will answer that question correctly, which it is. So now the question is, why did you know that at about row 50 is already enough to conclude that the value of 2,333 is prime? Why don't I have to go any further? And why does this have anything to do with proof by contradiction, obviously? What do you think? Yep. Square root, very good. So the square root of 2,333 is going to be less than 50. How do I know that? Because 50 times 50 is 2,500. I'm too lazy to actually find the square root of 2,333. So I just did an approximation. It's like, yeah, if we work all the way up to 50, we're good. Okay? But why the square root? Why, if I have tested every potential factor up to the square root of the number, and I do not find a, I do not confirm a multiple, do not identify an actual factor, why can't I stop at the square root?
If the number gets too big, so you go past it, right?
Right, but what do you mean by getting past it?
The value, like say 51 times, or for example, like your 50, 51 times 51 is going to be larger than 200 or 2,333, and it wouldn't work.
I think I know what you meant to say. So there's a precise way to say what you intended to say. Okay, so there's a precise way to do it. So the precise way to say it is for integers um, a, b, and c. Okay, a, b, and c. If a is the product of b and c, okay, make it more explicit. If a is the product of b and c, I shouldn't say integers because I don't want to deal with negative values. So let's go for natural numbers. Okay, so for natural numbers a, b, and c, if this is true, then okay, so this is the most important part. Then a is let me see, a is less no, the square root of a, b is less than, okay, there we go, b is less than or equal to the square root of a, or c is less than the square root of a. All right, so let's just look at this particular statement here and try to see how that applies to whether 2,333 is a prime number or not. Okay? So in this case, we're trying to ask Can I find two integers where their product equals to 2,333? Is that okay? And what this is saying is, if there was a factor other than the number n itself, and 1, then the factor, one of the factors, one of the numbers in the multiplication has to be less than or equal to the square root. Which means if I have tried up to the square root of the number and I could not find a factor, that means there's no such factor. Is that okay? It seems to make sense, right? Prove it. Prove that this is always the case. So when people prove something like this, they're going to come up with concrete examples, right? Like, oh, let's say A is 9, right? So 9 has 3 as its factor. So 9 equals to 3 times 3. 3 is less than or equal to the square root of 9. All right, it's true. Okay, cool. We can also look at the product of two prime numbers. So let's pick 7 and 11. Okay, so we look at 77, which is 7 times 11, or 11 times 7. It doesn't matter which way, because this says one of the two numbers that you form the product is going to be less than or equal to the square root of the number. So the square root of 77 is around, it's more than 8 and less than 9, right? So if we can test up to 9. So you can test 2, 3, 4, 5, 6, 7, 8, 9, and you cannot find any factor at that time. That confirms that 77 is a prime number. That's because 7 is less than or equal to the square root of 77. Is that okay? But can you conclusively say this has to be true? Well, you cannot just use examples to show that, well, since I cannot find a counterexample, what I claim here has to be true. Because that simply means that you have not touched an example that proves it is wrong yet. So now we want to actually go through a mathematical proof to say that, yep, we know this has to be true. But how do we do this? A direct proof is difficult. Okay, I do not know of a direct proof of this. But a proof by contradiction is actually pretty easy. So let's take a look at what part is the theorem and which part is the facts that are known to be true. All right, so what is given to you, okay, A, B, and C as natural numbers, that is part of what we know as iota. That's part of what we are given with, okay, because the properties of A, B, and C is a given. You cannot change that. And then the left-hand side of the implication is, well, okay, this particular implication, the implication itself is the theorem. It is what we want to prove. This part here. In other words, okay, this does not look like an implication. Let me turn it into an implication first, because it is kind of important to understand that we are looking at an implication. This implication is true. This is my theorem. This is the statement that I want to prove to be a theorem. Is that okay? So in the terminology that we have used so far, A, B, and C being natural numbers, that is what the Greek symbol psi is representing when we talk about proof by contradiction. Let me go back to that module and show you what I mean by that. This psi over here, this psi over here, that is what is known to be true, which means don't ask me, this is your given, okay? These are the given conditions. Phi, on the other hand, let me see here. So phi, on the other hand, is your actual theorem. In other words, we want to show that phi is going to be true as long as psi is true. Psi implies phi, okay? So in our example, this is our phi. Is that okay? And what we want to show, okay, we want to show that psi implies phi. Now, the fact that phi itself is an implication doesn't matter, okay? Because phi can be any expression, but in this case, phi itself is an implication. That shouldn't change anything. Are we good so far? Okay. So proof by contradiction, if I go back to the slide, wants you to show that if you combine what is given to be true, which is A, B, and C are all natural numbers, and then you negate the theorem, we'll talk about the negation of the theorem in just a little bit, that should imply false, which means the conjunction itself has to be false. Does that make sense? We talked about this, I think, last week sometime. Is that okay? All right. So now we go back to the text editor. We go, okay, so the first thing we need to do is to negate phi. So what is the negation of phi? Well, let me copy and paste because the negation is pretty easy to do if you can just negate the entire thing. And then we'll take a look at how to make a derivation out of that. Okay? All right, so now we look at this and go like, that doesn't seem very helpful. So let's figure out a way to work with this negation. So we'll say the first thing we do is we get rid of the implication, which means we negate whatever is on the left-hand side. And then we say or whatever is on the right-hand side. So the right-hand side is b is less than, okay, excuse me. I prefer to do it this way, if it's okay with you guys. Is that okay with you? It means exactly the same thing because A, B, and C are all natural numbers. So I can, if I say the square root of A is greater than, excuse me, if I say B is less than or equal to the square root of A, I really mean if you square both sides, they will still be maintaining the less than or equal to relationship, right? So I just prefer to write it this way, just personal preference in this case. And obviously this or needs double bar like so. And we are missing one close parenthesis. Okay. So when you look at this whole thing, um, even though there is an extra pair of parentheses starting here and ending here, well, since these are all ors, you don't need parentheses. So we now end up saying the negation of A equals to B times C, or B times B is less than or equal to A, or C times C is less than or equal to A. And now, I'm going to apply De Morgan's law. De Morgan's law is really easy to apply in this case because we have a negation of or. So that means I can quote unquote distribute the outer negation to each component that I'm oring, but in the process, I have to change the or to an and. So now I apply that. So we end up with double negation of A equals to B times C. We'll do the simplification in just a little bit. And B times B, it is not the case that B times B is less than or equal to A. And it is not the case that C times C is less than or equal to A. And then we go back and get rid of the double negation. This is what we end up with. So now we end up with a conjunction with three things in it. A is B times C. A is the product of B and C. And B times B is not less than or equal to A. Wait, if we say it is not the case that blah, blah, blah is less than or equal to blah, 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 is there a better way easier way to say this? I think so. Because I think the easier way to say this is to say, oh, what you really meant to say is B times B is greater than A. Right? I mean, it's just a whole lot more intuitive to look at it this way. So I'm going to change it to the other one too. It is not the case that blah, blah, blah is less than or equal to blah, blah, blah. Just make it a little bit easier to read. Like so. Do we see a problem here? Let's see. Okay, so let's say this conjunction is indeed true. Okay, so if this is indeed true, don't you think this is also saying B times C is going to be greater than A times A? Don't you think this is implied by the conjunction? Not looking at the first one, just looking at the second and the third component of the conjunction, and you just go like, well, since all of these are non-negative, so if I just use B times B as one component of the multiplication, use C times C as the other component of the same multiplication, and then pick up the other side of the inequality and also multiply those two together, the inequality should still hold, right? So let me just gonna say, okay, um, because this time I'm gonna show you the line of reasoning. So this, oops, and implies that this thing, this inequality has to be true. And then I use a little bit of algebra magic to say, I can now say, look at this as B times C times B times C because of the commutative law of multiplication, right? Okay. But then, because we also know that A equals to B times C, so now I look at B times C and go like, well, that's just A. So we end up with A times A is greater than A times A. You go like, uh-oh, what is the truth value of this greater than relation? It's just false. It doesn't matter what value A you choose to use. A times A is greater than A times A is guaranteed to be false. Okay, so this is indeed false. So now we have a contradiction because by, by negating phi is the theorem that we want to prove. This is the negation of the theorem that we want to prove. We end up with a conjunction. Now that conjunction by itself doesn't seem to be problematic. It's just the result of applying Boolean algebra. But when you look at what that conjunction is implying, it implies false. This conjunction implies false. So if the implication itself is going to be true, what can the conjunction be? What can imply false if the implication is true? Let me ask that question again because I know it sounds really confusing. And that's why I'm going to explain that. What can imply false when the implication itself is guaranteed to be true? So let me explain it using the truth table perspective. So we got X, we got Y, we got X implies Y. So the usual truth table thing, right? This is the truth table of implication. So what I'm asking is what implies in what implication that what can imply false where the implication itself is true. In other words, we're focusing on the rows where the implication is true. But at the same time, we also know the right-hand side of the implication is false. So we are looking for y being false, but the result of the implication being true. We only got one row meeting that requirement, which is the first row. So on that first row, x also has to be false. Is that okay? So that means if this is false, okay, if A times A is greater than A times A is false, you follow this chain backwards. Everything along this implication chain also has to be false. And it goes all the way to this, and then that is equivalent to the negation of phi, which means when you combine the negation of phi with what is known to be true, which is A and B and C are natural numbers, then we can show that the original phi, the theorem, has to be true. So this is another application of proof by contradiction. Is that okay? Does everybody kind of generally follow the steps to prove this particular theorem? Okay. So we are running out of time. I'm going to stop the lecture at this point. Um, on Wednesday, we are going to combine all of these techniques. So let me just kind of number the techniques. So we are basically looking at the trees in the forest. One is resolution, which is a mechanism to say, if you give me things like this, I can make it imply that thing over there. Okay, it's more or less syntactical. The second one is CNF, because resolution works really well when things are already in that format. Okay, and we have already shown that CNF may be cumbersome, but it's just as expressive as all Boolean expressions, which is great. The third one is proof by contradiction, which is basically saying, if you want me to prove blah, then I'm going to negate blah first, combine it with everything that is known to be true. If I somehow end up with false, okay, in this entire chain, then we know the original theorem is true. So those are the three key ingredients for our lecture on Wednesday, because we combine all of those things and say, okay, TAC, we are given these things in iota. How do we know this thing here is implied by those things in iota or not? Because we want a definitive answer. I don't want to give you the answer of, well, as far as I can search in this infinitely large haystack, the needle is not there. Instead of giving you those answers, I have to give you a definitive answer of the needle is there, which means it is a theorem, or the needle is not there, which means it is not a theorem. So I want to give you a conclusive answer based on what is given to be true to begin with. So that's going to be our exercise on Wednesday. It really helps to kind of read ahead of time and kind of go back to revisit things that I have used in today's lecture. All right, so I'll see you guys on Wednesday. And you got the homework, so start to do the homework.